welcome to our program, Astronomy for Everyone. We're still doing our show from our team members' homes, as you can see, but we hope to get back into the studio soon. The topic for this month's program is In the News. We haven't done this in a while, so we want to catch you up on some of the latest happenings in astronomy and space science. And here to tell us all about it is Stephen.
Welcome to Astronomy for Everyone. This is the July 2020 edition, and we're presenting In the News. We'll start with At the Surface of Water Worlds. Researchers at Arizona State University investigated what could be at the bottom of worlds with deep oceans. An extrasolar planet is at most a dot in the biggest of telescopes, but still, you can sometimes figure out the mass and diameter of these objects. That will give you the pressure at the bottom of an ocean. Temperature is a little harder, so what you have to do is you have to make guesses on what the radioactive sources are and the heat of formation of the planet, and then try a range. They used the Advanced Photon Source at the Department of Energy's Argonne National Lab. They also needed the pressure, and they got that with a diamond anvil. So what you do is you put in a mixture of water and rock, and you put it in the anvil, and then you shine light from two ultra-bright beams, X-ray beams, from the Advanced Photon source. What they found was that at the boundary of that the boundary between rock and water gets a bit fuzzy. There's no sharp boundary. Chemistry will work differently than we're used to in this situation, so this is a starting point for figuring out what sort of life might emerge. Exoplanet nurseries. The sharpest images from 4 years of work at the 8-meter Gemini South telescope in Chile were released last month. The targets are debris disks of young stars, presumably in the planet-forming stage. The strategy is to detect the dust first, since that's easier. The camera, the Gemini Planet Imager, blocks the central star with a coronagraph and takes advantage of the telescope's adaptive optics system that removes Earth's atmospheric blur. This allows images to show details as close as the Earth from each of the stars, as close as the Earth from the Sun from each of the stars. The survey targeted 104 stars, bright in the infrared, and found 26 with debris disks. The images of 19 previously known debris disks got improved images with this system. 7 of the 26 were previously unknown. These are members of a group called the Scorpius-Centaurus Stellar Association. They lie about 400 light years from Earth. They move together and are of the same age, which allows comparisons for study. These debris disks extend out in a range from 20 AU to 100 AU. Note that Neptune is about 30 AU from the Sun, the 1 AU being the distance from the Earth to the Sun. Of the 26 images obtained, 25 had holes around the central star, likely created by planets sweeping out rocks and dust. The instrument recorded polarized near-infrared light scattered by small dust particles, about 1 micron in size, likely the result of collisions among larger rocks in a debris disk. Polarized light from debris disks should be able to tell us something about how the dust is composed. For example, how much water is there? And that makes you wonder, which of these images most resembles our own early solar system? Now, in a related article, a nearby Neptune-sized planet was found. Data from NASA's Transiting Exoplanet Survey Satellite, TESS, you may have heard of TESS, has been used to detect a planet about as large as Neptune around a star called AU Microscopii. This planet has an upper limit of nearly 3 times the mass of Neptune. It has been measured to be about 8% larger than Neptune, and that's because when you're a Neptune, adding more mass doesn't make you a lot bigger, it makes you denser mostly. So the actual diameter doesn't increase that much, even if the mass is tripled. Anyway, it's currently thought to have formed further out from the star and migrated in while interacting with gas and dust in the system. An orbit takes just over a week. It's really fast, so it's really in close. This is an M-dwarf star, about 20 to 30 million years old, and of course it has a debris disk. It's located 32 light years away, so that's nearby in astronomical sort of distances. The star is part of the Beta Pictoris moving group, which also includes the hotter A-type star named Beta Pictoris, after which the moving group is named. And Beta Pictoris has 2 planets of its own and, of course, a debris disk. These are all the same age. These 2 planets that Beta Pictoris has probably haven't changed their orbits much at all, unlike AU Microscopii. The now-retired Spitzer Infrared Telescope was used to detect 2 transits that would have been missed by TESS due to the way that the TESS operates. It gets close to the Earth and transmits all its data. It takes time, and it's not taking pictures then. Ground-based telescope provided radial velocity measurements which give the planet's mass, or at least a boundary of it. Further ground-based data should help refine this value. Black hole or neutron star. On August 14, 2019, the LIGO-Virgo gravitational wave telescopes detected a merger that included either the heaviest neutron star or the very lightest black hole ever discovered. The heaviest neutron star that has been observed is 2.5 times the mass of the Sun. The lightest black hole ever observed is 5 times the mass of the Sun. There's a big range there. This object was 2.6 times the mass of the Sun. Either it's a black hole or a neutron star, but either way, it breaks a record. So, in this graphic, the blue circles at the top are gravitationally detected black hole masses. Highest on the scale is 80 times the mass of the Sun. The purple circles are black holes detected with telescopes, optical or radio. Down at the bottom, in yellow, are gravitationally detected neutron stars. Right in the center, left-right, are 2 objects that merged to form the black hole in this story. No visible light was detected by optical telescopes, or radio telescopes, which could push the guess towards a black hole. The only detection of light for one of these events, one of these gravitational events, was the merger of 2 neutron stars. It's a pretty messy affair when 2 neutron stars slam into each other. A black hole could possibly consume a neutron star in one bite, and then there would be nothing to see. But these objects would have spiraled into each other, so the neutron star could have been stretched out like spaghetti, in which case you would have seen something, maybe. The gravitational wave event is from the merger of 2 objects, and the other one was 9 times more massive. The final black hole mass is about 25 times the mass of the Sun. There is some mass loss due to the conversion to energy, that is, mass is converted into the energy of the gravitational waves that were then detected. Current theory has a difficult time explaining how this type of merger could take place ever. that we've detected one suggests that they happen much more frequently than predicted. Okay, raise your hand if you like aliens. The Breakthrough Listen initiative hopes to help in the search for extraterrestrial intelligence. They have released a catalog of over 700 one-of-everything targets. It should help in the search for something called technosignatures, signals from life as we know it. It is something like the Messier list of fuzzy objects from the 1700s, which helped astronomers identify classes of objects. This new list includes comets and galaxies, some mundane objects, but also rare and violent phenomena. The idea is to guide future surveys, that is SETI surveys, and serves as a reference for the field. For example, extrasolar planets might have been detected earlier if people were looking for solar systems that are very different from our own. No one was expecting giant Jupiter-sized planets right next to stars. If they had been, then considering that you can detect one of these things in a 6-inch telescope, it might have been discovered decades earlier. The list includes planets and moons, stars at every point in their life cycles, galaxies big and small, serene star clusters and blazing quasars, but also objects with the most extreme properties like stars with high and low metallicity, very distant quasars, fast-spinning pulsars, and densest galaxies. Anomalies like Tabby's star, which has a bizarre dimming behavior, or Oumuamua, the interstellar object that passed through our solar system in 2017. Stars with excess infrared radiation, possible waste heat from alien megastructures, although we also heard about dusty disks. Also, a set of control samples that are not expected to produce positive SETI results. What it does not include are transient objects that are too difficult to observe. This list can be used by new equipment as a shakedown cruise. The list comes with a discussion for classification of objects and anomalies, and plans for future observations. Project Listen looked for signals from the Kepler 160 system, which has an Earth-like planet around a Sun-like star. The new Exotica catalog is the centerpiece of Listen's efforts to expand the diversity of targets. The crucial principle behind it is the concept of survey breadth, that is, the diversity of objects observed during a program. This should help astronomers constrain the range of potential habitats for extraterrestrial intelligence, as well as rule out the possibility that any phenomena widely considered natural are in fact artificial. Conversely, it may identify natural events or confounding data, such as interference, that mimic the kinds of artificial signal that SETI researchers are on the lookout for.
There's some really interesting stories. We're going to take a quick break, and don't forget to send us an email if you have any questions. And coming up next with Term of the Month is John.
Thanks, Don. This month's term is circumpolar stars. A circumpolar star is a star as viewed from a given latitude on Earth that never sets below the horizon due to its apparent proximity to one of the celestial poles. This can be said for both the northern and southern hemispheres, but for today we'll just talk about the northern hemisphere. From your location, look towards the star Polaris. Circumpolar stars seem to rotate counterclockwise around Polaris for the entire night and every night of the year, and would be continuously visible throughout the day also, were they not overwhelmed by the sun's glare. The North Celestial Pole is located very close to the pole star Polaris, or the North Star. So from the northern hemisphere, all circumpolar stars appear to move around Polaris. Polaris itself remains almost stationary, always pointing north, and always at the same altitude or angle from the horizon, equal to the observer's latitude. Whether a star is circumpolar depends upon the observer's latitude, or roughly 42 degrees here in the Detroit area. Since the altitude of the North Star always equals the observer's latitude, any star whose angular distance from the celestial pole or Polaris here in the northern hemisphere will be circumpolar if the angular degree is less than the observer's latitude. For example, if the observer's latitude is 42 degrees north, any star will be circumpolar if it is less than 42 degrees from the center celestial pole. All circumpolar stars lie within a relative circumpolar circle whose radius equals the observer's latitude. As the Earth rotates daily on its axis, stars from the north celestial pole appear to rotate in large circles. Stars located very close to the celestial poles rotate in small circles. Depending on the observer's latitude on Earth, some stars, the circumpolar ones, are close enough to the celestial pole to remain continuously above the horizon, while other stars dip below the horizon for some portions of their daily circular path. The circumpolar stars appear to lie within a circle that is centered at the celestial pole and tangential to the horizon. At the Earth's north pole, the north celestial pole is directly overhead, and all stars that are visible, that is, all the stars in the northern celestial hemisphere, are circumpolar. As one travels south, the north celestial pole moves towards the northern horizon. More and more stars that are at a distance from it begin to disappear below the horizon for some portion of their daily orbit, and the circle containing the remaining circumpolar stars becomes increasingly small. At the equator, the circle vanishes to a single point, the celestial pole itself, which lies on the horizon, and thus there are effectively no circumpolar stars at all. A constellation made up entirely of circumpolar stars is also called circumpolar. For most of the United States, these are above 40 degrees north latitude. This star trail photo was taken by club member Gordon Hansen. He took 30 10-minute exposures for a total of 3 hours and then stacked the images with a program called Star Stack, spelled with an X. With this type of image, all you need is a DSLR camera and a tripod and some way to start your camera and have it go to bulb for 10 minutes. Another way you can do it is by just doing 30-second exposures and doing them for a total of 3 hours. Term of the month, circumpolar stars. And now back to you, Don.
To continue with more interesting stories, here's Stephen.
So there's more than one way of looking at this sort of calculation. In a related but independent recent article from the University of Nottingham, an estimate of the number of active civilization in our galaxy was calculated. Tom Westby explains that the two astrobiological Copernican limits are that intelligent life forms in less than 5 billion years, or after about 5 billion years, similar to on Earth, where a communicating civilization formed after 4.5 billion years. That's us. The strong criteria, whereby the metal content equal to that of the Sun is needed, and the Sun is, relatively speaking, quite metal rich. We calculate that there should be around 36 active civilizations in our galaxy, assuming that they last about 100 years as technological civilizations. That's how long we have lasted so far as a technological civilization. The average distance to the nearest of these stars and planets should be 17,000 light years away. We can't currently communicate that far, we find that if we find that intelligent life is common, it would suggest that civilizations last longer. Christopher Cancellas, there you go, Christopher Cancellas. Christopher Cancellas explains that there should be at least a few dozen active civilizations in our galaxy under the assumption that it takes 5 billions for intelligent life to form on other planets as on Earth. And last up, something about the moon. Researchers at the Tokyo Institute of Technology, the University of Florida, the Carnegie Institution for Science, Towson University, and the NASA Johnson Space Center and the University of New Mexico have released a paper describing clues as to why the moon is different on the near side versus the far side, and why the moon has had geological activity so recent in its history. They are linked to something called creep. That's spelled with a K. K is for potassium, TH is for thorium, and uranium are also parts of creep. These are radioactive. Inside the moon, they can melt rock with heat, and also by reducing the melting temperature of rock so that it can ooze out onto the surface. These elements appear co-localized mostly on the near side of the moon, in the Maria, the black parts of the moon that were named for seas in, because it was thought that, seas on Earth and all of that sort of stuff. This explains why the side of the moon that with the most Maria, which is the near side, is so different from the other side. The heat generation also explains how the moon stayed hot enough to have geological activity for so long, that is to about 1 billion years ago. So it had been active for 3.5 billion years. Evidence for this kind of non-symmetric, self-amplifying activity might possibly be found on other moons in our solar system. So, stay tuned for that. Don Glaser ends our show with What's Up in the Night Sky. Off to you, Don.
What's up in tonight's sky for July 2020? We'll begin with the star we know best. The sun on the 1st rises at 5:59 a.m., setting at 9:13 p.m. But by the end of the month, the sun will rise at 6:23 and set at 8:52. Next, the moon. We begin with a full moon on the 5th, followed by the last quarter on the 12th, new moon on the 20th, and first quarter on the 27th. Planet Report. This month is a virtual feast for planetary observers. At midnight on July 1st, Jupiter stands 15 degrees above the southeastern horizon, shining at magnitude -2.7, and by 1 a.m., it's at its highest elevation at about 30 degrees. It reaches opposition when it appears opposite in our sky from the sun on the 14th. The planet's disk measures 48 arc seconds across, giving telescopic viewers a great opportunity to observe atmospheric detail. The Galilean moons, Io, Europa, Ganymede, and Callisto, are also shining brightly. Especially look for transits of not only the 4 moons, but their shadows as well. On the 1st, Saturn lies just 6 degrees east of Jupiter, increasing to 8 degrees by the 14th. Rising just 20 minutes after the Jovian world, Saturn reaches opposition on the 20th, shining at magnitude 0.1. its axis is tilted 21 degrees towards Earth, displaying the northern side of the rings, giving us great views of the rings, including the outer A ring, the brighter B ring, and the inner C ring. In a small scope, you'll also be able to see the Cassini division, which separates the A and B rings. Rising just after 1 a.m. on the 1st, Mars shines at magnitude minus 0.5, and by the 31st, standing 45 degrees above the horizon, it shines at magnitude minus 1.1. As its disk size increases during the month, finer surface detail comes into view in a telescope. A quick program note. Our September show will be about the red planet, ahead of its opposition on October 6th. Don't miss it. Mercury rises around 5:30 a.m. on the 19th and shines at magnitude 0.8 and can be seen 5 degrees to the right of the waning crescent moon. By the 25th, it brightens to magnitude minus 0.1, and on the 31st, it's at minus 0.7 and forms a triangle with the two brightest stars in Gemini, Castor and Pollux. Venus on the 1st stands 8 degrees above the horizon, shining at magnitude minus 4.6, with two well-known neighbors, the Hyades and Pleiades star clusters. On the 12th, it passes 1 degree above Aldebaran in Taurus. By the 31st, Venus passes 2 degrees south of the star Zeta Tauri, the tip of the southern horn of the Great Bull. Next, Neptune and Uranus. Neptune can be found in the dim constellation Aquarius, rising about 1 a.m. A few hours later, it is easy to see using binoculars in a dark country sky, shining at magnitude 7.9. A telescopic view will show a 2 arc-second diameter bluish disk. On the 1st, Uranus rises 2 hours before dawn in the constellation Aries the Ram, shining at magnitude 5.8. A telescope will reveal a bluish-green disk covering 3.5 arcseconds in diameter. Now that size is equal to the size of Mars when it's at its farthest point from Earth. And that's what's up in the night sky for July 2020. Thanks for watching.